Did you know that one of the planets in our solar system spins backwards compared to the others? Yep, you heard that right. While every other planet in our solar system rotates from west to east, following their orbital motion around the Sun, this sideways planet has a unique distinction of rotating from east to west, going the opposite direction. And no, it's not Venus, which rotates incredibly slowly, but is still technically rotating in the correct direction. It's Uranus. So why does Uranus rotate the way it does? In other words, what's behind the retrograde rotation of Uranus? The answer is pretty mind-boggling. You might have thought that something as massive as a planet would have an easy time spinning up or slowing down. But believe it or not, even something as large as Uranus can be affected by something as simple as a glancing blow. But before we get into that, let's look at some of the other effects of this retrograde rotation. As you probably already know, Uranus is extremely tilted on its side, with an axial tilt of 98 degrees. Now, don't get confused. An axial tilt refers to how far off a planet is rotating on its axis relative to its orbital plane, which is the flat plane in which it orbits the Sun. If a planet is rotating perfectly straight on its axis, like Earth, its tilt would be 0 degrees. If it was rotating on its side, like on its orbital path, its tilt would be 90 degrees. And if it was rotating upside down relative to its orbital path, it would again have a tilt of 180 degrees. So because Uranus is so highly tilted, most of the sunlight that hits it is either polarizing or near the poles. That's why Uranus has such extreme seasons. Each pole experiences 6 years of daylight, followed by 6 years of darkness. Now it's generally accepted that this extreme tilt is what caused Uranus's sideways magnetic field. Let me explain. A planet's magnetic field is generated deep within its core, through the process called the dynamo effect. Now, you don't have to worry about what exactly causes this. Just think of it as a bunch of churning electrically charged fluids deep within the planet that creates an electromagnetic field. Here's the important part. For the magnetic field to work, the planet needs to be rotating. That's because the magnetic field is created by electrically charged fluids moving through the planet. Since these fluids are electrically neutral overall, the only way for them to move is relative to the planet's rotation. Take Earth for example. Our magnetic field wouldn't work if Earth wasn't rotating. So because Uranus is rotating sideways, this sets the general direction of its magnetic field, which is almost perpendicular to the Sun. Now, you might be wondering why the magnetic field doesn't just line up perfectly with the rotational axis. Since the entire planet is rotating around that axis, well, there are 2 reasons for that. First, the planet's atmosphere is creating some drag on the fluids that generate the magnetic field, pulling it somewhat towards the Sun. And second, the Sun itself is exerting a magnetic force on the planet. Because Uranus is so massive, its magnetic field extends far out past its atmosphere and reaches out to meet the solar wind. In other words, Uranus's magnetic field is being stretched out by the Sun. Now, these 2 forces are counteracting each other, with the atmosphere pulling the magnetic field away from the Sun, and the Sun itself pulling the magnetic field back towards it. These 2 opposing forces are balancing each other out, resulting in the magnetic field being pulled into a slight angle. Now, as you might imagine, having a magnetic field that's nearly perpendicular to the Sun causes quite a few problems. First, Uranus's magnetosphere is enormous. Uranus's magnetic field extends more than 24,000 kilometers out into space. To put that into perspective, Earth's magnetosphere only extends 60 kilometers out into space. This enormous magnetosphere is caused by the interaction between the solar wind and the magnetic field. This region is filled with tons of charged particles that can easily strip away Uranus's thin atmosphere. And sure enough, billions of years ago, the solar wind managed to strip away all of Uranus's atmosphere, turning it into a desert wasteland. Luckily for us, this didn't happen until after the formation of the other planets. Otherwise, the solar wind would have stripped away their atmospheres too. Okay, now let's finally talk about why Uranus rotates the way it does. At first, astronomers believed that the retrograde rotation of Uranus could have been caused by the same thing that caused its extreme tilt, a massive collision early in the solar system's history. But over the years, scientists realized that this couldn't be the whole story. That's because they estimated that such a collision would have completely knocked Uranus off its axis, whereas Uranus still retains roughly 90 degrees of its axial tilt. So whatever caused Uranus's retrograde rotation must have been a glancing blow rather than a head-on collision. But this still leaves us with another question. How do you create a glancing blow powerful enough to rotate a planet the size of Uranus? Well, scientists think it would take a lot of small impacts, thousands, or even millions of small asteroids impacting the planet. But the problem with this theory is that it doesn't explain why Uranus's tilt isn't 180 degrees. Remember, for Uranus's tilt to be 180 degrees, the collisions would have to push all of the planet's material past the center of mass. And while it's possible, it's unlikely to happen in even a glancing blow. According to computer simulations, it takes a very specific series of collisions to get a planet's tilt to be exactly 180 degrees. So, unless the collisions that formed Uranus were extremely precise, it's unlikely that its tilt would be exactly 180 degrees. So if the retrograde rotation of Uranus was caused by a bunch of small impacts, why did it end up with an axial tilt of 98 degrees instead of 180 degrees? Well, the answer might actually lie in the type of object that impacted Uranus. Scientists recently found out that many of the objects in the early solar system weren't asteroids, but rather water-rich dwarf planets similar to Pluto. This may not seem like a big difference, but it's actually quite significant. You see, unlike rocky asteroids, these icy objects would have shattered upon impact, leaving behind a thin layer of ice on top of Uranus's surface. This ice would have acted as a lubricant, reducing the amount of friction on the planet's surface and allowing it to rotate much faster. Eventually, the ice would have evaporated into space, leaving Uranus with its extreme tilt and sideways magnetic field. There's also some evidence that supports this theory. Computer simulations of Uranus's early history suggest that it could have easily ended up with its current tilt if it was bombarded by icy objects. But this raises another question. Where did all of these icy objects come from? That's because, while there were likely plenty of asteroids in the early solar system, there weren't any known bodies that were massive enough to leave the other planets with their observed tilts. Well, it turns out that these icy objects were likely a natural byproduct of the giant gas giants themselves. See, when Jupiter and Saturn formed, their intense gravity literally ripped apart countless icy bodies in the outer solar system, sending them hurtling towards Uranus and Neptune. So rather than having these icy objects come from the Kuiper Belt, scientists believe they came from the giant gas giants themselves. But why is Uranus the only planet with a retrograde rotation? Well, it all comes down to where it formed. Uranus formed in an area that had enough gravity to capture these rogue icy bodies. On the other hand, Neptune formed slightly farther away, where there was a bit too much energy for these objects to remain bound to its gravity. But the reason why Uranus ended up with an extreme tilt is a matter of pure chance. Imagine you have a box full of marbles and you start tilting it to one side. If you tilt it slightly, the marbles will settle into a relatively flat pile. But if you continue to increase the tilt, eventually the marbles will reach the point of no return and collapse on one side. Well, that's essentially what happened to Uranus. The icy objects pushed it past the point of no return, causing it to collapse on its side. So there you have it, the weird retrograde rotation of Uranus, explained in 100 seconds. If you enjoyed this episode, make sure to leave a like and subscribe for more. Thanks for watching till the end, and I'll see you next time.